Hey everyone, welcome back to another video by Camroom 5. In today's video we're going to continue reversible reactions and we'll study Le Chatelier's principle to see how equilibriums are affected. This principle states that whenever an equilibrium is disturbed, remember last time we talked about disturbing an equilibrium? So it says whenever an equilibrium is disturbed, it moves in a certain direction, either goes to the left or goes to the right. So it moves in a certain direction to regain stability. That is not just chemical equilibrium, but that is any kind of equilibria. But we are going to study it with reference to chemical equilibrium. So how can it be disturbed? It could be disturbed by change in amount or concentration of reactants or products, change in temperature, or change in pressure. What will happen? So either it goes to the right doing forward reaction or towards the left doing reverse reaction. So what happens when there's a change in concentration? So obviously when we talk about change in concentration, we are talking about amount in moles of the reactants or the products. Let's go back to the Haber equation, which is 1 mole of nitrogen reacting with 3 moles of gaseous hydrogen to produce 2 moles of ammonia. All of these reactants are gaseous and we often think about their pressure, but let's imagine their concentrations, right? Imagine the reactants and products are in equilibrium with each other. The seesaw represents the equilibrium. On the left we have the reactants and on the right we have the products. Nitrogen and hydrogen represent the reactants, while 2 moles of ammonia are the products. The seesaw, which is in a stable condition, represents the stable chemical equilibrium. Now, imagine this stable chemical equilibrium has been disturbed. How has it been disturbed? So, imagine we are adding more hydrogen and nitrogen gas, or you can say hydrogen or nitrogen. So we are adding the reactants. When the reactants are added, there would be more amount and the equilibrium is disturbed. So technically, the chemical equilibrium will try to compensate. The chemical equilibrium will move towards the right to produce more ammonia. When it's moving towards the right, you can say that the forward reaction is favored and reverse reaction is not favored here. So when the forward reaction will be favored, as a result of the forward reaction, more ammonia will be produced, so the chemical equilibrium will regain stability. Imagine in another scenario, what we are doing is we are removing some of the ammonia from a chemical equilibrium container. So when we remove ammonia, the amount of ammonia in the container decreases and again there is less stability. So to compensate, the equilibrium will again try to make more ammonia so that they can become equal. So the forward reaction will be favored again. When the forward reaction will be favored, you can say the equilibrium moves towards the right so that more ammonia can be produced, and where more ammonia can be produced, obviously the amounts will become stable again and the dynamic equilibrium will become stable. In a third scenario, for example, this time you are adding more ammonia. Imagine you had ammonia in some other container and you bring it and you add it here. So the amount of ammonia increases and that is again causing destability. So what happens is that the equilibrium will move towards the backward direction, or you can say the reverse reaction will be favored. The equilibrium moves towards the left and the reverse reaction will be favored. When the reverse reaction is favored, ammonia will be used up and nitrogen, hydrogen will be produced. As ammonia is used up in the reverse reaction, the amount will decrease again, and the amount of ammonia will return to its original value. Now let's talk about another condition, which is the change in temperature. When we talk about temperature and reversible reactions, we should remember there are two kinds of chemical reactions. Endothermic reactions, which absorb heat energy and they have a positive enthalpy, while exothermic reactions release heat energy and they have a negative enthalpy. In endothermic reactions, the forward reaction is basically endothermic. So don't forget that endothermic reaction means that the forward is endothermic, but the reverse would be exothermic, because reverse reaction is actually the opposite of the forward one. And when you talk about the other kind of reaction, which is the exothermic reaction, don't forget that as the exothermic reaction is forward, the reverse would be opposite, which means the reverse would be endothermic reaction. So if some reaction is exothermic, its reverse is endothermic. And if some reaction is endo, its reverse is going to be exo. Now 2 points are important. High temperature always favors the endothermic reaction, whichever it is, whether it's the forward or the reverse. So in endothermic reaction it will favor the forward, but the reverse in exo. The second point is low temperature always favors the exothermic reaction. And by exothermic we mean that the normal forward reaction of exothermic ones, but the reverse one of the endothermic ones. It becomes harder to remember, so I have a mnemonic, which is exotil, EXOTIL, which means in exothermic reactions, temperature increase shifts the equilibrium towards left, and opposite would be that in the same exothermic reactions, the temperature decrease will shift the equilibrium towards the right. So exotil means temperature increase left. We have another word for endothermic reaction, which is endotir, TIR, which stands for in endothermic reactions, temperature increase shifts equilibrium to right, and the opposite would be in endothermic, temperature decrease shifts equilibrium to left. So remember exotil and endotir. Now let's go back to the Haber equation, which is an exothermic forward reaction. So obviously the reverse would be endothermic. If it's exothermic reaction, we use the word exotil, which means temperature increase shifts equilibrium to left, and temperature decrease shifts equilibrium to right. Now let's study it using graphical analysis, which is very common in the O-level examination. Remember, left means ammonia will be used up in reverse reaction, and right means ammonia will be made up. Let's put temperature on the x-axis and the amount and the percentage of ammonia on the y-axis. Left of the x-axis means low temperatures, and right on the x-axis means very high temperatures. You know what's low temperature? Low temperature means temperature decrease, and high temperature means temperature increase, while y-axis means the amount of ammonia. At low temperatures, temperature is decreasing. So exotil tells us that equilibrium goes to the right, which means forward reaction. At low temperature, temperature decreases and equilibrium goes to the right, because we know this from the exotil. And when equilibrium goes to the right, what will happen? Ammonia will be made. So at low temperatures, equilibrium moves to the right as its exothermic forward reaction, and as a result of right direction, more ammonia will be made up, So ammonia increases in percentage. In the opposite case, at high temperatures, remember Axotil tells us at high temperatures, when temperature increases, equilibrium moves towards the left, and left means reverse direction. So less ammonia will be there because it's an exothermic forward reaction and it follows the Axotil. So high temperature will shift the equilibrium to left, which means ammonia will be used up. So there will be less ammonia in the container and the graph looks like this. So I hope this idea is clear to us, and the next video will talk about the role of pressure. Stay tuned, guys.